One of the most important rules that you learned in Calc 1 was called the chain rule. So it works when you're composing two functions. So let's say we have one function g of x, and then we take whatever comes out of that function and we we plug that into some other function f. Then the name of that function we call f compose g of x, right? So we make a new function, you could call it h of x, that starts with some value x, plugs it into g, and then whatever comes out of g we plug into f. That's the composition. So our question is, what is the derivative of this composition? So, well, if you think about it, what we're doing, we start with our value x, and then we have some function g, and then so we plug in some value x, and out comes the value g of x. Then we take that value g of x and we go over here and we plug it into f. So here's our value g of x. We have some function f that does something different. So this is the function g, here's the function f. We plug g of x into f and we get out f of g of x. That's our function h of x. So if we want to know what the derivative of h is, we should look at what happens to a tiny change. So if we make a small change, delta x, right, then that should give us approximately, if we use our tangent line approximation, we'll get an output, right, a change in the output g. Delta g will be g prime of x times delta x. Okay, so then we'll go over here and we'll plug in g of x. We'll make this change here, delta g, and then according to the tangent line approximation, then delta h is going to be f prime g of x, right, times delta g. So there's the change in the input to f times the slope of f gives the change in the output h, but delta g is actually g prime of x delta x. So what happened, to get the derivative of a composition, basically we took the derivative of the two functions and we multiplied them together. So the derivative of the composition is the product of the derivatives. And you recognize that as the chain rule. And what's going on is you're looking at how does the output change. Well, that's the slope of the outside function, right? Evaluate the inside function times the change in the inside function, but the change in the inside function is the slope of the inside function times the change in x, and so this should be then be whatever dh dx is. That's the derivative. In our case, now we're going to have functions that have possibly more than one input and more than one output, but we'll have a similar situation. So we'll have in our original domain, right, we'll apply some function g, and that will give us maybe a vector in some new set, and then we'll apply some function f, and that will finally give us our answer. So if we have some value here, then this could be some vector, but the output would be g at that vector, right? And then we're going to take that. So we'll take that thing and we'll plug it into f, and so then our output will be f of g of x in general. And if we make a small change in x, then that's going to lead to a small change in g, right? So that would be equal to the total derivative of this function g times the change in x. Okay, and then over here we'll get the total derivative of our function f evaluated at g of x times the total derivative of g, right, times delta x. That will be our derivative. So if we call this whole composition h, starting from our initial using g and then f, if we call that whole composition h, then the total derivative of h is going to be the total derivative of f evaluated at g of x times the total derivative of our function g. So it's just matrix multiplication. In Calc 1, each derivative was a 1-by-1 matrix, so it was just multiplying derivatives in general. So this is just sort of the more general case of our derivative formula that h prime at x was equal to f prime at g of x times g prime of x. Okay, let's see how that works. We have here two functions. I've got a function f. F has three inputs, x, y, and z, and two outputs. And then I have this function r. R has two inputs and three outputs. So this would work just right if I started with some number u and v and I plugged them into r. Then I would get three numbers, x, y, and z, and then I could plug those into f. Right? And I would get those two outputs in f. Maybe I could call them S and T here. And those are the two outputs, so you could get S and T. So if we call this whole composition, the whole chain that starts with u and v and gives you st, then if we call that h, and we want to find the derivative of that function h, we know that there are two inputs to h and two outputs to h, so h should be a 2 by 2 matrix, right? Well, what 2 by 2 matrix? It should be the matrix for the total derivative of f times the matrix for the total derivative of r. Let's see. F has three inputs, two outputs, so it should be a 2 by 3 matrix. And r has three outputs, two inputs, so it should be a 3 by 2 matrix. And let's put in the entries here. So for f, we have the partial of f. Let's see, the partial of s with respect to x would be 3x squared. And the partial of s with respect to y is 1. And the partial of s with respect to z is minus 2z. And then the partial of f with respect to, of t here with respect to x is y. And the partial of t with respect to y is x. And the partial of t with respect to z is positive 2z. So there is the total derivative of f. Now we need to figure out the total derivative of r. So r is a 3 by 2 matrix. Let's see. So here's our first output. We could call it x. The partial of that with respect to u is going to be 3 cos u cos v. Cos v. And I should have left myself a little more room here. Let me just kind of erase that a little bit. Okay, go back. So cos u cos v, and then the partial of this first one with respect to v, the derivative of cosine v is minus sine v, so we get negative 3 sine u sine v. And now the next one, the partial with respect to u, is 3 cos u sine v, and then the partial with respect to v, since the derivative of sine v is cosine v, we have 3 sine u cosine v. And finally, this last entry, the partial with respect to u is minus 3 sine u, and the partial of 3 cosine u with respect to v, well, it's constant as far as v is concerned, so that's 0. Okay, so to find the total derivative for h, notice that if you take a 2 by 3 times a 3 by 2, you get a 2 by 2 matrix, just like we were expecting, right? Because this entire function h has two inputs and two outputs, so its total derivative should be 2 by 2. Let's multiply this. We get 3x squared times 3 cosine u cosine v, and plus 3 cosine u sine v, and plus 6z sine u. That's our first entry. Now our next entry over is going to be 3x squared times negative 3 sine u sine v would be minus 9x squared sine u sine v, plus 1 times 3 sine u cosine v, so that would be plus 3 sine u cosine v. And so there are the two entries in my first row. Now to get the entries in the second row, we'll take this row with this column. We're going to get 3y times 3 cosine u cosine v cosine v, and we'll get x times this, so plus 3x times cosine u sine v, and then minus 6z sine u. Okay, so there's 3 of our 4 entries in this 2 by 2 matrix. The last one, we'll take this row with the second column. We get negative 3y sine u sine v, negative 3y sine u sine v, and then x times 3 sine u cosine v would be plus 3x sine u cosine v. And we have our total derivative matrix. We have each of the entries.